Hello, everyone. So today I'll talk to you about diffractive optical neural networks that are designed by deep learning. Basically, an optical diffractive network is formed by individual layers of transmissive or reflective elements, where each pixel here is treated as a learnable parameter. So based on a certain task, which could be an image classification task, or an imaging task, or any other optical system task that you want to achieve between the input and output relationship, this black box formed of these layers is trained using data, using deep learning methods, error backpropagation methods. As an example, with a computer using deep learning and error backpropagation methods, you can train a sequence of diffractive layers in order to all-optically classify images. In this example, I'm sharing with you MNIST handwritten digits that this diffractive network has learned to classify. If we, for example, place here a handwritten digit 5, most of the photons will be arriving at this detector 5 assigned to this image class. So this set of layers have been, pardon me, trained till their layers here are adjusted to route the photons of a given image class to the correct detector. And this is done through error backpropagation methods, which I'll describe in the next few slides, till the diffractive network is converged. After that point, we fabricate it. In addition to statistical inference, you can also design deterministic optical black boxes composed of diffractive layers to perform a certain task, such as imaging. I'll also give you some examples of this. One of the interesting things about diffractive networks is that, especially as an optical inference machine, they're composed of passive layers. Except the illumination and the detector part, the layers do not consume power. So it's a low power system. The calculations of object encoding and the spatial features of the object to make all optical inference, these are happening through diffraction of light. That's why the computation is done through the speed of light through diffraction. These are also scalable solutions because you can design larger wafers, larger area systems, and benefit from the parallelism of optics. The communication between layers is happening through spherical waves. And that's the network that is formed through trainable matter. Individual coefficients, the amplitude and phase of these individual pixels are trainable, which means the amplitude and phase information of one of those spherical waves emerging from these points and how it's impacting the interference at other points of the other neurons, it's determined by basically these trainable layers and the previous layers and the diffraction inference coming from the previous layers. So the math is different than standard electronic neural nets, although there is some resemblance. One interesting feature here is that you can encode information in the amplitude and phase and/or phase of the input plane because it's a coherent processor. That is especially interesting for the phase channel, because linear combinations of different phase functions do not result in linear superposition of the coherent waves at the output plane. Apart from that, the nonlinearity that we have in the system is at the detection plane here. And these layers do not, in this implementation, do not have any nonlinear coefficients. They're ignored. So once the design is done through a computer, we then fabricate them. Depending on the wavelength of operation of this coherent processor, you can select different fabrication methods. Many of the results that I'll share with you today have been fabricated after their design using standard 3D printers, because we've selected terahertz part of the spectrum to demonstrate the efficacy of these systems. For example, this is a design that processes handwritten digits, 5 layers put together as shown here. A few tens of wavelength separation between the layers in this case. And this one is another data class that's a second diffractive network that is similar dimensions to process fashion products all optically. And this one is another design which is a very thin optical imaging system where the distance between the object and the image plane is only a few tens of wavelengths. The design task changes all these pixels in a unique way in the sense that the elements are shaping up in a unique manner to solve the task at hand. For example, for imaging, you have a totally different solution than image classification shown in here. And this is our experimental test bed. We use a terahertz source. This is where the diffractive network goes. And we're looking at the detector positions assigned to different image classes to determine if it's successful or not. This is one of those zoomed in images of one of those 3D printed diffractive networks after it's converged. In this case, we're looking at classification of handwritten digits. And I'll share with you results after its training with test objects that were never seen by the network before. So there are 10,000 test objects that were never used during the training phase. That's why it's statistical inference in the sense that this is not simple mode matching, as you expect, for example, in integrated photonic circuits. It's actually more than a simple mode matcher in the sense that these new test images, whether it's a 0 or a 2 or a 4, 5, whatever, these are different handwritten digits, and the network did not know their presence before. And that's why it's not doing a simple deterministic task in this case. These are some examples from our experimental results. For example, if you take a NUV2 at the input, the output plane, most of the photons went to the correct detector. This is the detector that we assigned to class 2. Similar, for example, if you take an 8 at the input, at the output plane in this coherent processor, most of the photons went to this detector, which was assigned to class 8. And these are showing you the signal intensities. Using a simple max operation, the maximum signal, you're revealing all optically the input object class. In this case, in this example, objects were encoded in the amplitude channel, and the diffractive layers were phase-only diffractive layers, meaning that the trainable parameters there were only the phase elements, the thickness values of the layers. These are the confusion matrices. This is the experimental, and this is the design phase. There are 10,000 elements here. You have for MNIST approximately 92% with this initial design, and these are some experimental results again. So I'll share with you some results later on how to push this number with all optical diffractive networks to much higher. For MNIST data, right now we're close to 99%. Of course, when we started, it was about 91, 92%, and there are different ways to improve it, as I'll share with you today. Next, we took this to a more challenging data set. This is called Fashion MNIST. It's another publicly available data set. As you can see, some examples are shown here. It's composed of 10 data classes: sneakers, bags, boots, t-shirts, and dresses, etc. So each one of them is a single class that we were tasked to separate into 10 unique data classes with this thing. Here, we used phase encoding, meaning that because this is a coherent system, we can encode the information in the amplitude or phase. And in this case, the fashion images were encoded at the input aperture through phase information. This is what we converged after designing this system with 50,000 of these images. And next, I'll share with you some blind testing inference results coming from the remaining 10,000 test objects, approximately 1,000 objects per class. For example, this is a dress at the input never seen by the diffractive network before, and at the output, most of the photons beautifully end up in this detector 3 assigned to class 3. Similarly, this is a sneaker, class 5. Most of the photons ended up in this detector, all optically inferring the data class through this phase encoding. This is the confusion matrix for this task, which is more difficult than the handwritten digit classification. That's why the accuracy here was initially as shown here, about 81%. through 5 layers and phase-only modulation. Later, I'll share with you results that push this by another 10% now. For fashion MNIST, we're about 91% inference accuracy. These were some of the initial results. So if you look at the training of these initial results, you can see that we've used to penalize the diffractive network and to train the system and to train each one of these individual pixels, we used mean square error. That's why if you look at the output detector, we were having, for a given input class, some sort of a uniform illumination within the target detector area, which was a little bit restrictive for the diffractive network. Later, we switched a different type of a loss function to train the network, cross-entropy loss, which essentially releases that restriction of the uniformity of the field intensity within this detector and makes it acceptable to have some speckled pattern as long as a lot of the photons at the output, most of the photons at the output, compared to the remainder of these 9 detectors, fall to the correct detector. So all of a sudden, it becomes speckly, but still it achieves a maximum signal for the correct detector class. So it's a different way of training the diffractive system. And this actually helped us quite a bit in terms of our inference accuracy. For example, these are now MNIST results from approximately 91 to 92% accuracy. We've reached to more than 97% with just this new loss function with a very similar 5-layer diffractive network. Layer-to-layer separation here is delta Z. Layer-to-layer separation is about 40 lambda. So it's a very compact network. In the visible part of the spectrum, this would be less than 1 millimeter in thickness, as an example. So a decent performance was achieved, more than 97% for MNIST. And for fashion products, those 10 different classes of clothing, we've achieved close to 89%, slightly better than 89% blind inference accuracy with those 10,000 blind testing data set. So an interesting feature of this diffractive system is that there is not a nonlinear neuron function at any given layer. The nonlinearity, surface nonlinearities are so weak, and of course we're ignoring those. But there's still depth feature of a diffractive optical network, meaning that even though you can squeeze mathematically the entire 5-layer network into a single matrix multiplication, it doesn't mean that free space with a single diffractive layer, single layer between the input and output planes would be able to satisfy the same mathematical function that those 5 layers can approximately achieve. So there's depth to the diffractive networks in the form of converging to better solutions as you increase the number of layers. This is a good example of this depth feature empirically demonstrated for MNIST and fashion MNIST results with 2 different loss functions. Softmax cross entropy, like before I've shown you, or mean square error. As a function of number of layers for different loss functions and different data classes, you can clearly see that the inference accuracy is improving as the number of layers. But more than that, there's a logarithmic improvement in beyond the generalization capability of the network. There's a logarithmic improvement in the power efficiency and signal to contrast. Power efficiency is simply for the correct label detector. What is the efficiency? As you can see, there's a logarithmic increase in the power efficiency at the correct detector for a given label as you increase the number of layers. And this one is a single contrast, meaning that this is the percentage improvement with respect to the second competing detector. So this I sub SC is the intensity at the strongest competitive detector. It changes from input to input randomly. But even that difference, which is the signal contrast as we define, is logarithmically improving as the number of layers increase. We have done numerous analysis on different tasks. It's always the same conclusion. As you increase the number of layers, your approximation power of a diffractive network formed by multiple layers beats the approximation power of a single layer or low number of layers. So this is the conclusion. So next I'll share with you some additional design strategies to make this framework to generalize better and perform better for various different classification tasks. And here I'll talk about differential design and class-specific design and the combination, which is class-specific differential design. Rather than assigning a single detector per data class, here in this differential design strategy, we assign two different detectors as a pair to a single data class. And we're looking at differential signal. The network is panelized to maximize, if it cannot maximize, the differential signal, the signal difference between, for example, this positive and this negative detector assigned to data class 1, so on and so forth. You can also design class-specific networks where you divide some of the subclasses into one network and another network takes care of the rest. So these are interesting ways to kind of benefit from the parallelism of this free space network. So in this simple configuration, let's warm up. Instead of using 10 detectors, one per class, here there are 20 detectors. It's still a low number of detectors, and every one of those classes is assigned one positive and one negative detector. These are virtually positive, virtually negative detectors. And we do differential analysis with a very simple normalized differential signal between these two detectors, so that we introduce the negative contrast that we don't have at the intensity level at the output detector. So it gives us an additional polarity, which is going to help us with our signal-to-noise ratio. If you train the diffractive network like this, let's say 5 layers, same as before, phase-only modulation, same thing, but let's say there are 10 different object classes. This kind of encoding scheme performs much better than standard encoding scheme. It's actually highlighted here for MNIST dataset, for fashion MNIST dataset, and CFAR10, another dataset, which is quite challenging for, in general, all optical inference methods. So you're seeing here the blind testing result of these 20 detectors. As you can see, these are the positive detectors, these are the negative detectors, and you're looking at a differential signal. If you look at the differential signal for this input, the only positive polarity is assigned to this 5. All of them are showing a negative polarity, meaning that the negative detector had more intensity or more signal per detector. So it's showing you a beautiful advantage of this additional plus-minus polarity that we've introduced. Same idea applies for fashion. If you look at it, the correct class has the positive polarity, and the rest is by and large negative. For CFAR10, a similar thing applies here. Most of them are negative polarity, incorrect classes, and the dominant positive polarity is the correct class. So this is the differential scheme at the cost of having 20 detectors. You can have here better inference. We also done different kinds of comparisons. We've given the other standard method, instead of 10, 20 detectors to see if it's coming from just the number of detectors. That's not the case, actually. This differential encoding scheme beats 20 detectors where 2 detectors are assigned to a given class in a standard method without the polarity introduced. So in addition to this, you can also have differential diffractive networks that are class specific. Here, for example, you have, again, 20 detectors, but you have negative detectors and positive detectors assigned to different diffractive networks. The idea, again, is to maximize the normalized signal. And this is just a class-specific differential, pardon me, just a class-specific diffractive network where you divided the detectors at the output into 2 different diffractive networks. Some classes are handled by one diffractive network, and some subset of classes are handled by different diffractive network. These are different combinations of schemes that you can do. And in the next slide, I'm comparing in this slide, I'm comparing the performance with 3 different data sets of these different combinations. For example, for MNIST, fashion, and CFAR10, the winner is always class-specific differential detectors or diffractive networks. So the green here, the green curve, is showing you the performance of class-specific differential diffractive networks. As you have more and more subset of diffractive networks handling different data classes, you have better inference accuracy. The previous results at the very beginning that I've shown were these. Basically, these were the performance coming from cross-entropy loss for a single diffractive network without any differential encoding. So from these initial points, you can go to these green points by using class-specific and differential encoding scheme, which achieves close to maybe 99% for MNIST, and somewhere between 91 and 92% for fashion, and slightly above 50% for CFAR10. Another interesting observation that we had is you can take these differential diffractive networks and have them project their patterns onto the same output detector plane. Here what you're looking at is multiple classifiers, diffractive classifiers, that project their results, and at the output there is some averaging ensemble model formed by averaging coming from these independently trained diffractive network models. What we've seen that is with the differential scheme, the orange curves here, we can benefit significantly from this ensemble of three classifiers. In this case, for example, to hit more than 51% for CFAR10. So these are independently optimized systems that project their light onto a common detector output plane to benefit from the power of these different units. They are identical in terms of their architecture, but because of the randomness of the training process, they're not exactly doing the same thing. During the training, they've optimized in a slightly different manner with different output patterns. That's why they benefit each other. This is the summary of all of these results. Basically, compared to the standard design, which assigns a single diffractive network and 10 detectors, one per class, differential designs win, and differential class-specific designs seem to be the winner of all of them, together with the ensemble of three independent differential designs, as shown here. So these were all optical designs, basically composed of many diffractive layers working together. You can also think of hybrid systems that can benefit from diffractive networks as a front end. So one of the very interesting aspects of diffractive networks, in especially machine vision, is the use of trainable diffractive layers as a front end for electronic neural nets. So this is actually a very interesting aspect, because we believe that diffractive systems that are trained for a certain task form a superset to lenses. So here we are jointly optimizing a diffractive system to work with an electronic digital neural net, let's say a modest one, without depth, with only a few layers, or maybe even less, to see if this hybrid system can perform competitive tasks, image classification tasks, with the help of the front end. In this case, there's still a certain loss function, classification loss function, and both the electronic neural net and the diffractive layers, individual pixels, are being panelized through airback propagation as a joint system to work for the task at hand. So this means the diffractive network knows right now that it's delivering information to a digital network that is exactly, specifically trained to handle that information for the classification task. One of the biggest advantages of this system is it can actually compress information in a certain way through the diffractive network. If you look at, for example, MNIST or fashion MNIST images, these are composed of 28 by 28 pixels on the order of 700, 800 pixels. If you look at here, the inference accuracy of the hybrid system, where the diffractive network is the front end, is quite flat, even though you undersample it, where the detector array has only 10 by 10 pixels. So compared to roughly 800 pixels of the input, you only have here 100 pixels to pass to the electronic neural net. So this is a major feature of this collaboration between diffractive network and an electronic network. And one other thing here is that these results are coming from a very simple electronic neural net. It's a single fully connected electronic layer. Even that can handle this kind of compression to achieve a very nice result. For example, if you take a perfect lens, with this information loss, the electronic layer cannot help with the classification. It drops significantly because here you lost information. But the orange coming from the diffractive trainable front end is helping you with that task. Another very exciting comparison is compared to deeper electronic networks, the hybrid system coming from the trainable diffractive front end is significantly more power efficient. So in terms of the energy consumption per image classification task, a perfect lens with a modest network versus diffractive network with a fully connected layer, there is a logarithmic advantage in terms of energy consumption per image, while the accuracy is also retained. So this is actually highlighting the advantages of trainable front ends composed of diffractive layers to work with electronic backends, especially if we believe for low power systems that need to work with low pixel count imaging systems. We believe that the front end that is designed for a specific task would be much better than simple lens-based system, and much better to handle especially the few pixels that you have, the constraints that you have in terms of the power requirements per classification, etc. So this is a symbiotic relationship that we formed here and demonstrated with the front end and the back end working together to compress information so that still the accuracy of the classification is retained with undersampling. These were examples of diffractive network designs that were geared towards statistical inference and image classification, and eventually forming hybrid systems with electronic neural nets. In the last 1 minute or so, I'd like to briefly talk to you about how we can also use diffractive networks to design optical components in non-standard manner, So, and that's where data-driven optical component design through deep learning comes into picture. So here we're trying to do mode matching or a deterministic task between input and output pair. One example is actually a thin imaging system. For example, this network that we formed here is performing an imaging task with maybe a few tens of lambda separation between the input plane and the output plane. And this was trained by showing the diffractive system various different images and penalizing the network if the output does not match those images in terms of the training cycle. And if you look at what we've learned here, these are quite different than the image classification networks that are shown about. In fact, if you zoom into one of these diffractive networks, you would see that these are pockets of phase islands, very much like mimicking almost an imaging fiber bundle in a sense. So it's forming to mitigate diffraction between the input and output layer through these phase pockets, phase islands. And we've tested this with terahertz wavelengths, and these are showing you imaging performance of these types of compact multi-layer learned diffractive imaging systems. In addition to diffractive imaging, you can also design different kinds of filter functions with diffractive networks. Basically, in a recent work, we have utilized diffractive networks to harness the spectrum of broadband sources. In this example, this diffractive network is tasked with processing of the frequencies of a broadband source in the form of creation of a filter or wavelength division multiplexing or different kinds of tasks that you need for harnessing the spectral content of broadband sources. It's also a deterministic task, but by treating individual pixels and their thickness here as a variable, you can actually train this to filter the broadband spectrum in unique ways and form solutions to your input-output relationships that you want to achieve. We've tested this with several different 3D printed networks. This one, for example, is one of those where the input radiation here is channeled to 4 different apertures at the network output, each of which has a different passband. So this is an example of wavelength division multiplexing at different sub-regions of the output plane. In the interest of time, I'll stop here and refer you to the to the recent paper that came out last year, at the end of last year, which is describing to you the design of task-specific optical systems using basically broadband diffractive networks that can handle broadband radiation. So thank you again for the opportunity, and hope the conference was a great success. Thanks.